Okay. Hi, everyone. Thank you so much for joining in. So you're being here. I think we are recording the session right now. So uh, the message must have popped up on your screen, and your being here is a consent that you are allowing us to record the session. So we are having a webinar today, and let me share my screen. So um, thank you so much for using the chat function and for being very interactive. Today we are having AuthorAID webinar on logistic regression analysis in the project analytical model, a practical methodological approach. And for this, you can see Felix in the screen. Hi, Felix. He's here. He's a very prominent research and data scientist and also our AuthorAID steward. So thank you so much for joining in. First of all, I would like to share some housekeeping rules. Number one is we are recording the session, like I mentioned earlier, and your participant indicates that you're providing us consent for the recording. The second is closed caption is available. You can click on the three dots at the bottom of your screen and then click on the CC button. If you have any difficulty, any technical issues throughout the session about how to use the interactive features or anything else, you can contact me at this email address, asta.subedi@inabstractinfo. And we would like to request you to mute yourself if you are not talking so that we could be very clear throughout the session. And you can use raise your hand feature in the participant panel if you'd like to ask a question during the Q&A. Q&A will happen at the end of the session. And questions and comments can also be submitted at any time during the session using the chat function. Another is we are very vibrant networking space here at AuthorAID, so you can use all of the interactive tools and also keep on interacting and talking with each other in the chat itself. Before handing it over to Felix, I would like to introduce him. He is an accomplished researcher, analytics, and data science professional with a demonstrated ability to develop and implement data-driven solutions in the urban and health sector. With over 10 years of experience in teaching and leading epidemiological, biostatistical, and data science projects from descriptive to predictive analytics. He also works as a research scientist, scientific writer, and epidemiologist at the Center of Health and Development CSD, which was founded after years of international research collaboration between the University of Port Harcourt and Dalla Lana School of Public Health at the University of Toronto, Canada, and more recently, the University of Ottawa, Canada. The center aims to develop human and organizational capacity for health-related research and quality healthcare provision in Niger Delta region of Nigeria, built on sustainable local structure and data collaboration. And he's also a doctoral student at the Durban University of Technology in South Africa. And I would like to now hand it over to Felix. Yeah, over to you, Felix.
Yeah, thank you so much, Asta, for that wonderful introduction. So I'm so happy to have so many people join this meeting. And like it was said, it's going to be a practical methodological approach. I will try my best to make that happen. But another thing I'm going to do, because logistic regression sometimes can be a very tricky subject, so I will try as much as possible not to be too fast, but I'm very happy that the session is recorded so that if you miss any part, then you could go back and watch it, especially the practical demonstrations, which I'll be doing at the end using the SPSS statistical software. All right, now we proceed. I'm going to share my screen right away. So you can see my presentation slide, I guess.
Yes, we can.
Okay, thank you. So I want to answer this important question. When do you need logistic regression analysis in your project analytical model? Because logistic regression, it's quite popular, but one aspect I have seen in my career is a lot of times you wonder, when do I need, to put in the logistic regression? It's a part of an inferential statistics, meaning a type of statistics that you use to answer some of your research hypothesis, So, but there are many others. It's not only logistic regression, but if I want to use logistic regression, when do I need to bring it in, or what are the parameters that I need to meet to show that, oh, now I need logistic regression, and what is it like? How do I fit my data to be able to do this, and how do I do it? So I think I will be trying, my best to actually, answer all of these questions. So my name is Felix Emeka Anyiam, and Asta has introduced me. So I'm an AuthorAID steward, and I'm happy to be taking this session with you. At the end of the session, we'll have some question and answer, so you can reserve that, for the end. So understanding the logistic regression model itself. There are other terms, that are applicable apart from logistic regression. Sometimes you could hear binomial logistic regression. Sometimes you could hear binary logistic regression. So binomial, binary, or sometimes they just say logistic regression. They are all one and the same thing. And because they are coming from that word bi, meaning two. So the observation we mean here, it's actually the dependent variable, the main outcome for your study, the reason why you're doing that work. Is it to determine the prevalence of malaria? They have malaria, they don't have malaria. Is it to determine the prevalence of cancer? They have cancer, they don't have cancer, So the binary, which is two observations, two categories, or the binomial, it deals with your dependent variable. That is why for you to run a logistic regression or a binary logistic regression, that's one of the conditions that you have to meet. It means your dependent variable has to be two categories. If your dependent variable or the outcome of your research is not dependent, is not, two categories, you won't be able to run a logistic regression. That's why it's called a binary logistic regression, meaning there has to be two sides, of that variable. All right, but for your independent variables, it doesn't really matter. For the independent variables, meaning the explanatory variables that are responsible for the patient or the participant having susceptibility to the outcome you're interested in, those ones, they don't need to have two categories. For example, an explanatory variable can be exposure, to excessive sound pressure level. And you can have different measures of the sound pressure level. You can have mild, you can have moderate, you can have severe. Now, exposure to the explanatory variable, which is sound pressure level, can make the participant susceptible to the dependent variable, which is noise-induced hearing loss. So the noise-induced hearing loss, which is your dependent variable, you can categorize it into two. They have noise-induced hearing loss, or they don't have noise-induced hearing loss, which is yes and no. All right, so that is one of the things you have to bear in mind when you want to run a logistic regression. Are you able to dichotomize? Are you able to put your dependent variable, the main outcome for your research, are you able to put it into two values? If you're not able to put it into two values, then that outcome does not fit for a logistic regression. All right, like I mentioned, the two possible outcomes depending on the dependent variable, it can be a yes and a no, can be a success or a failure, can be a heads or a tail, like for probability, can be positive or negative, like HIV status. Either they are positive or they are negative. There's no in between. So if your study, is determining the prevalence of HIV in that community, then that would fit because your dependent variable, which is the prevalence of HIV, can be positive or negative. And one of the things too you also have to appreciate is the dependent variable. They are usually categorical data. Categorical data in the sense that they have categories. They are not numbers. They are not numerical. So if your dependent variable, the main outcome variable for your study, they are numbers, numerical data, then it doesn't fit into logistic regression. It fits into another type of regression, which I would show you, much later. But for logistic regression, that data has to be categorical, meaning it has to have categories, not numbers. Like if you're talking about gender, it has a male and a female, malaria, yes, and noise-induced hearing loss, yes, and so these are categories, and when you analyze categories like this, in the descriptive aspect of the analysis, they come out as frequency and percentages. So in our second slide, an independent variable can be things that is changed. Things sometimes you can have influence on. But the dependent variable is that variable that is affected by the independent variable, like I mentioned before. If you look at this picture that I have here, the amount of water, it's independent, is explanatory. You can decide how much water you put into the plant. But you don't have a decision on how big that plant will be, or how many leaves the plant will have, or if the plant is going to die or live. You don't have the power to make that decision. Your job is to water the plants. So watering the plant is the independent variable. That's the explanatory variable. That's the variable you have power over, the variable you can change. But what happens after that? The result of the modification or the introduction of the independent variable, that one you don't have control over. So for logistic regression, this dependent variable, like I mentioned before, has to be dichotomized. So you have the independent variable, which is the amount of water on the plant. The dependent variable outcome can be dead or alive. It can be big or small. It can be short or tall, So the explanatory or independent variable fits, and the dependent variable depends on that explanatory variable to make a decision. And I have some examples below, as you can see. An example of a dependent variable, noise-induced hearing loss, either they have it, yes or no. Quality of life, either it is poor or it is good. Cancer, either they have cancer or they don't have cancer. Weight gain, either they have weight gain or not. And the independent variables that can be responsible for this outcome, for noise-induced hearing loss, sound exposure. So excessive sound exposure can determine whether they will have noise-induced hearing loss or not. Comorbidities like hypertension, diabetes, and the rest of them can decide if a participant quality of life is good or poor, because some studies have shown that the more the comorbidities, the poorer the quality of life. Excessive exposure to radioactivity can determine whether they have cancer or not. And healthy diets can determine whether they have weight gain or not. You see, so your job is to introduce the independent variable, the sound exposure, but you will not be able to determine whether they have noise-induced hearing loss or not. So you don't have control over your dependent variable, but you could have control over your independent variable. Sometimes some independent variable can be found in the environment. You don't have control over it. Like sometimes exposure to sound or noise can be in the environment. So you don't have control over that one. But exposure to radioactivity, especially if the person works in a hospital, the person can actually make a decision, to minimize the exposure, level, or the patient can also make a decision on how to eat. So some explanatory variable you can have power in controlling, some you would not be able to. Okay, so let's move to the next slide. And I'm very happy that you are appreciating the dependent and the independent, which is also called explanatory. Dependent is also called your outcome. Now, like I mentioned, for logistic regression, you're dealing with categorical data, the ones that when you analyze them, you have frequency and percentages. You're not dealing with numbers. However, if your dependent variable or your outcome is numbers, numeric, then you would not be doing a logistic regression. You'll be doing what they call linear, regression, where you'll be having a linear relationship because your independent variable, they are numbers. Your dependent variable, they are numbers. So the dependent variable is not dichotomized. They are numbers. So you can only do a linear relationship, and the statistical test that is used is called the Pearson's correlational coefficient. So what it does is measures the strength and direction of the linear relationship, okay? So for example, if we're looking at a continuous variable like age and another continuous variable like weight, so you want to see if the age is increasing, is the weight also increasing? So that's a linear relationship. All right. So if the participant age is increasing, is their weight also increasing? So it will be reading the numbers. Increasing age, does it lead to increasing weight or does it lead to decreasing weight? All right. And it has values, okay, between 0 and 1. So 0 means very weak because when you run the analysis of linear regression, it gives you numbers between 0 and 1. 0 can mean like 0%, 1 can mean like 100%, so it gives you a range in between. So anything that is less than 5 is usually considered weak. But anything that is greater than 7 is usually considered strong. So depending on the number it gives you. So if you run that linear relationship and it gives you like 0.4, that's a positive relationship because there's no minus to it. So if you have 0.4, that is in the range of weak, all right? 0.4 is in the range of fairly strong. I think less than 4 is weak. So if it gives you like 0.4, that's fairly strong, also called moderate. And if it's a positive number, what that means is as the age is increasing, the weight is also increasing, but the relationship is moderate. If it gives you minus 0.19, that's a negative relationship, meaning as the age is increasing, the weight is decreasing. So that participant may be having issues with malnutrition. All right, so that is how the linear relationship behaves. Either one is increasing, one variable is increasing, the other one is decreasing, or one variable is increasing, the other one is also increasing. To represent linear relationship, oftentimes we use what they call the scattered plots, okay, to represent it. So this is an example that you can actually see here. Okay, it's an example you can actually see here. So when you see this kind of chart, it tells you that there's a strong linear relationship. So meaning as the independent variable is increasing, the dependent outcome is also increasing strongly. But when the chart is facing this way, it's a negative linear relationship, meaning as the independent variable is increasing, the dependent variable is decreasing. Okay? This is increase too, but it is weak because you can see the points are scattered around the line, not as close as the strong one. The same thing with this. So linear relationship are represented using scattered plots. Now, if you look at this, that's an example of a table if you're doing a linear relationship, a linear regression, all right? It gives you the Pearson's coefficient, which is arrow. It gives you the arrow square. Arrow square measures the percentage of the independent that is correlating with the dependent or the outcome. It gives you a p-value, whether it's significant or not, and it gives you a confidence interval for the coefficient. So if we're looking at this now, the independent variable here is the serum-free thyroxine, which is the T4. The outcome is the TSH, all right, which is the thyroid stimulating hormone. So based on this Pearson's correlational coefficient, 0.266 is weak from what I showed you before, and it is negative. So this could mean that as the serum-free thyroxine, which is the T4, is increasing, the thyroid stimulating hormone is decreasing. So as T4 is increasing, TSH is decreasing. That's why you have a minus 0.266. And this association is weak. However, it is statistically significant. The same thing with this one. Okay? So that is how the linear relationship works. This is the scattered plot again. From this line, and from this value, which is weak, 0.23, but it's not negative, but it's weak. So this can tell you that as the PM10 is increasing, PM2.5 is also increasing. That's why you have a positive sign here. And that relationship, this weak relationship, is statistically significant, as you can see in the p-value. So I needed to put all this together because I wanted us to distinguish between the linear relationship and the logistic regression, the linear regression and the logistic regression. So now we are dealt with the linear regression and you know when to use it. Now, when do you use the logistic regression? Now, one is when you want to calculate odds of an occurrence or you want to predict the chance of an event happening. If you're not predicting odds, you may not need logistic regression. I will explain that further using the chart using the table that I have below. All right, it helps you to quantify relationship in terms of probabilities and odds. Now, if you look at this table, it's a table from one of my analysis. Now, I'm looking at association between participants' self-reported occurrence of tinnitus. Tinnitus is ringing in the ear. So self-reported because they were asked, these are musicians. So they were asked, do you have ringing in your ears? They say yes or no. That's why it is self-reported because the tinnitus diagnosis was not gotten based on the examination of an audiologist. It was gotten based on what the participants, told me. So occurrence of tinnitus is already dichotomized. Either they have or they don't have, yes or no. Then the noise-induced hearing loss, which I measured using a pure tone audiometry. So I have those that have noise-induced hearing loss and those that don't. So for this table, my null hypothesis will be there is no association between self-reported occurrence of tinnitus and the occurrence or the prevalence of noise-induced hearing loss. Then I ran the analysis. As you can see here, I used the chi-square. Now, when you're running an inferential statistics, when you're associating categorical variables, as long as you want to check for differences in percentages, you're using the chi-square, which is appropriate. That is what is here. That's the symbol of a chi-square. All right, so that is the most appropriate test to use when you are checking for differences in percentages. So what differences in percentages am I checking? If you look at the noise-induced hearing loss, I have a yes. So I want to see between those that have tinnitus, yes, and those that do not have tinnitus, no. Which category have more noise-induced hearing loss? And is that difference statistically significant? Then you can use a chi-square for that. So as you can see here, those that said they have ringing in their ears, 72.94% of them have noise-induced hearing loss. That's a lot. But for those that said they don't have ringing in their ears, only 27.06 have noise-induced hearing loss. So what does that tell you? It tells you that more participants with noise-induced hearing loss was observed in those that have tinnitus. 72.94 against 27.06. Now, this difference you're observing now, 72.94 against 27.06, is it statistically significant? Is 72.94 significantly higher than 27.06? So because you want to check for differences in these percentages, the appropriate test of significance to use is the chi-square, which is what I did. So the chi-square was 70.38, and the p-value was less than 0.05, which is the cutoff. So it's 0.001. Now, from this significant value, I can reject my null hypothesis that says there's no significant difference between occurrence of tinnitus and noise-induced hearing loss, because from my chi-square and p-value, I can see that 72.94 is truly significantly higher than 27.06. So that is the first stage. I can decide to end here, and that's it. I can decide to end it right here. I don't have to go further. But if you end here, you will not be able to tell the odds of occurrence, which helps you predict the chance of an event happening. That's where the logistic regression comes in. The chi-square only tells you, oh, 72.94 is significantly higher than 27.06. That's where it ends. But what is the probability? What is the odds of someone that have tinnitus having noise-induced hearing loss? That's a very important question to answer, especially for public health practitioners. We want to know the odds of someone that have tinnitus coming down with noise-induced hearing loss. Chi-square will not be able to answer that. That's where logistic regression comes in. It gives you the ability to calculate odds. It gives you the ability to measure odds of occurrence. That way you can actually predict the probability of something happening. You know, so in this case now, I did the bivariate logistic regression and I have an odds ratio because it comes out as an odds ratio. So I have an odds ratio of 14.96. 14.96. So why my chi-square tells me, oh, 72.94 is significantly higher than 27.06, which means there were more proportion of those that have noise-induced hearing loss, you know, being in the group that have tinnitus. But my logistic regression now tells me something further and interesting. It tells me that those that said they have occurrence of tinnitus are 14.96 times more likely or more at odds of having noise-induced hearing loss. That adds a more, you know, a more information, adds more information to your analysis, and we help policymakers be able to make a decision quickly, So that's when to use the logistic regression. When you want to calculate odds, you want to know the odds of occurrence. Like in this case now, I can boldly say, oh, if someone has tinnitus, they are 14.96 times more likely to come down with noise-induced hearing loss, unlike someone that doesn't have tinnitus, and that's a lot of odds. 14, approximately 15 is a lot of odds. So it means that we have to now take measure to ensure that people, that have tinnitus are treated quickly before it exacerbates to noise-induced hearing loss. Okay, so we move to the next slide. So what are the other reasons? I've stated the main reason. There are other reasons, okay, when you can use logistic regression. Your dependent variable should be measured on a dichotomous or binary scale too, like I mentioned initially, like male and female, like you can see here. If you look at all these values, they are dichotomous. They are splitted into two: yes, no, true, false, agree, disagree, male, female, urban, rural. But you can agree with me that honesty is the best policy as an independent variable can be 5. Meaning you can have strongly agree, undecided, disagree, and strongly disagree. So it can be 5 Likert scale. But if I want to use honesty is the best policy as a dependent variable for logistic regression, I have to dichotomize it to agree and disagree. That's one of the rules. Okay. Vishal, let me take your question quickly. Vishal. Yeah, Vishal. Okay.
Yeah, please explain the confidence interval part in that odds ratio. That's my question.
Yeah, you said what?
Confidence interval. Yeah, previous slide.
Okay, the previous, yeah. The confidence interval is for the
Yeah,
odds ratio.
Yes, yes.
Yes, the confidence interval is for the odds ratio. Yes, yeah. Is that clear?
Yes.
Okay. All right. So let's progress. Thank you. Okay. So, however, you can have a dependent variable that is not dichotomous, meaning it's not 2. It has an ordinal scale, like this one that I've mentioned, which is honesty is the best policy. If you decide that you don't want to dichotomize honesty as a dependent variable to agree and disagree, you want to use it as an ordinal scale, strongly agree, undecided, disagree, strongly disagree, then you're going to be using another type of regression, which is the ordinal regression analysis. That's not what I'm focusing on today. I'm focusing on logistic regression analysis, where you have to dichotomize your dependent or outcome variable, right? Okay, so building the logistic regression model, there are things you have to have in mind before you build your logistic regression model. One of the things is your dependent variable has to be dichotomous, 2 groups. I've mentioned that over and over again. Secondly, your independent variables, you don't need to worry. They can be 2, they can be more. You don't need to worry about that. Now, you have to ensure there's absence of multi-collinearity, meaning the model assumes that independent variables are truly independent. And you have to test for multi-collinearity. I'll show you how to test for that. Okay? And for you to run a logistic regression, from the rule, it says that your variance inflation factor, which is the VIF, has to be lower than 5. Because anything between 5 and 10 means there's multi-collinearity in your data, meaning your data is not independent. Sorry, your independent variables are truly not independent. Okay? So apart from testing for multi-collinearity, another thing you could test for is the Hosmer-Lemshow, which is another model you can also assess before you can use the logistic regression model. So if you run the HL and your p-value is less than 0.05, meaning it's statistically significant, it means the model is a poor fit for logistic regression. That is the rule. So it means the goodness of fit, the p-value in the goodness of fit, which you run through the HL, should not be statistically significant. The p should be greater than 0.05. So if you don't meet these two criteria when you run the model, then you can just run the chi-square and leave it there. You don't need to progress to the bivariant logistic regression. So I will show you in practical terms how these things work. So this is the rule or the steps. First, in your data, you run descriptive statistics. For the categorical variables, you run the frequency percentages. For the continuous variable, you run the mean, standard deviation. Then you can move over to run the inferential statistics, which is based on your null hypothesis. For the inferential statistics, you run the chi-square because you're checking for differences in percentages like I showed you. Now, variables that are, so once you've run the chi-square, some associations will be significant, some will not. Now, if you don't want to stop in the chi-square, like I mentioned, you want to move ahead to see the odds of that association, you can do a model check, the multi-collinearity, then the HL to test for the goodness of fit, to be able to put it into the logistic regression model. Once both of them fit, then the variables that are significant or statistically significant in the chi-square, you put them inside the bivariant logistic regression model. And those that are statistically significant in the bivariant logistic regression model, you put them into the multivariant logistic regression model. What the multivariant logistic regression model actually tests is to confirm that the variables that are significant in the bivariant are truly independent. So because in the bivariant, you run one independent variable and the dependent variable one at a time. But in the multivariant, you put all the significant variables in the bivariant together in a pool. And those that are significant in the bivariant, if they come out significant in the multivariant, it means they are truly independent. That's why they are called independent variable, meaning that they should not be confounding with each other, meaning one variable should not be influencing the other variable. Every variable should be independent. They should be standing on their own. So that is how the order, flows. So we are going to be practicalizing this. So I'm going to stop this now so that I can show you in practical terms how this works using SPSS. But first, I'm going to be using a table, from my PhD. So I titled it demonstration table. Now, this is social demographic characteristics. If you look at this first part, you will see this is the descriptive statistics. So you would see unweighted frequency and weighted frequency, then weighted percentage. Well, you would not need to do this if you are not using a DHS data, because I'm actually using a DHS data for my PhD. The demographic of a data, the large data set. And if you're using a DHS data, imagine a country like Nigeria that we have over 200 million people. And the data for Nigeria from DHS may be 200, 300,000, 400,000. I mean, what is 400,000 compared to 200 million? That's a small fraction, but it is allowed, because you usually follow a sampling process. So it's allowed. But if you're using the DHS data, you have to wait. You have to do what they call weighting. That weighting helps normalize the data. So meaning if you have 300,000, 400,000, when you weight that data, it helps that 300,000 to be representative of the entire population that was supposed to be interviewed for that work. So the weighting and the unweighted may not apply to you. So if your work is not a DHS data, you don't have to do weighted frequency and unweighted frequency, okay? So you will probably have this first frequency, which you will just call frequency. All right, but in my own case, I have to wait because of the nature of the data. All right. For age was a continuous variable in the data. So because it's a continuous variable, I had to do the mean and the standard deviation. Then I did a range. So the participants were between 15 years and 64. So these are the frequencies and the percentages. It's a large data. So after cleaning, I had over 500,000 participants, but it was actually more because I had to do a lot of data cleaning. All right. So this is what the descriptive statistics looks like. It gives you frequency and percentages for the categorical. It gives you means and standard deviations for the continuous. So I have descriptive statistics for social demographic characteristics. I have descriptive statistics for awareness and knowledge of sexually transmitted infection and HIV. So these are the questions. So I have a yes and a no. Ever heard of AIDS? Yes, a no. Can reduce your risk of getting yes and a no. So these are the variable names. These are the values. So for descriptive statistics, I have socioeconomic support, which measures their wealth index. Then I had a pie chart. If you want to have a pie chart, you can. So I also measure the knowledge and the use of HIV self-test. So what I colored red, that is my dependent variable. That is the main outcome for this study. My work is trying to look at factors that will improve HIV self-testing amongst vulnerable populations. That means female sex workers, men that have sex with men, those in prison, transgender, So those are the vulnerable young girls, vulnerable long truck distance driver, So I'm looking at strategies that will improve HIV self-testing, which is a type of testing you do in your home. You don't have to go to the health facility to do it. So just to see if you can actually detect factors that will improve these, then you may, have a way to encourage this group of people to actually self-test than going to the health facility, because a lot of them have issues with stigma. That's why they don't go to the health facility to do a HIV test. So they can actually self-test, at home and know their status. So this is the main outcome for my work. If they've used HIV self-test kit before, never, yes. So I have a yes and a no. So you see the yes is more over 300,000, then the no is like, the yes is like 9,000 something, then the no is over 300,000. So I have a pie chart for that. So this is my main outcome. So this is the first association that I'm doing. I'm using a chi-square, which is the first step, like I mentioned, so you have the chi-square. Now, if you now want to do the model fit that I mentioned, so this is the SPSS. So these are my data. So they are all here. So these are my data. All right, the one that I want to use for this practice. Then these are the variable name. You can actually look at the label, what they mean. So these are the things that they mean, so this is for sex, the male and the female, marital status and the rest of them, So if we go to the slide in this path, which is the first part that I talked about, doing the multicollinearity. The multicollinearity, you actually go in the aspect of the linear regression, and you click your statistics, you will see it there in XPSS. So let's check for the multicollinearity of the variables and see if they fit for our model. So you go to analyze, regression, then the linear. And when you go to linear, the dependent variable for my work is HIV self-testing, which is this, HIV self-testing. That's my dependent variable. Either they self-test or they don't self-test. So the independent variable, you will put all the variables that are concerned inside the independent variable. Then you go to statistics. Then you choose the collinearity diagnostic. So that is it. So you choose that. You can pick a confidence interval if you want, but it's not important. But this is the main guy here to check for your multicollinearity. Then you continue, then you say, okay. So what it does is going to give you, the VIF, which I mentioned here as the variance inflation factor, but it has to be less than 1. So if we look at the result for the SPSS, our VIF for the variables that we put in, they are all less than 2, 1.1 points, so it means this our model is fit for logistic regression. Okay, so the VIF is lower, Then you can also do the second one that I told you, which is the Holzschmidt-Lemshow, the HL2, just to see the model fit, So how you do that one, you go to analyze regression, but this time you go to binary logistic. That's where you get it from. Then you can put the HIV self-testing here in your dependent variable. Then your independent variables, you can just pick, pick the ones that you need, whichever ones you need, you can put them here in the covariate. Then when you go to options, you will see it there. When you go to options, the HL, the goodness of fit is there. So you can also request for confidence interval too. Then you can continue and say, okay, then you will see it there. It's going to show and it's going to give you a significant value. So this is it, the HL. So this is 0.005, 0.000, which is actually significant, So in real case scenario, I would not be running the logistic regression for this model because it is statistically significant. The goodness of fit for the chi-square, it's applicable. You can run a chi-square, but I may not proceed, for the logistic regression because HL, the P has to be greater than 0.05. And in this case, it's less than 0.05. Okay, that's if we're using the real data, but this is just a practice data that I'm using. So that's how you run the tool models, okay? So we are in the chi-square. Like I mentioned, before you progress to the logistic regression, you have to do your chi-square first. So I'm doing the chi-square. So in this table now, my null hypothesis can be there's no association between the social demographic characteristics and the HIV self-testing. So that's what the null hypothesis is here. So as you can see, this is my main outcome. If they've tested using the HIV self-testing kit, yes and a no. So the gender, significant, current marital status is significant. So what this significance simply means, because of the large data, I have a prevalence for those that I've tested. If you look at this currently residing with husband. You see, those that are residing with their husbands that I've tested is 2.3. Those that are not residing is 4.1. So what does that tell you? It means that those that are not living with their partners are more, have a higher prevalence in testing for, HIV. 4.1 against 2.3, and it's statistically significant using the chi-square. So what the chi-square does, it just tells us that the difference in the percentage, that's 4.1, is significantly higher than 2.3. That's all chi-square tells you. It tells you differences in percentages, and that's all. And that's not so much, it doesn't give so much information. It just tells you, the 4.1 is higher than 2.3. So meaning that those that do not live with their husbands will most likely test more than those that live with their husband. And you know why? Because those that are not living with a partner may be more sexually active with several, other persons. But someone that is already married may just be with their partner. So they may not be at risk of HIV. But the ones that are not living with a partner or husband may see themselves as, having risk, especially when they are sexually active, So that's what the chi-square tells us. And if you look at the place of residence, you can see this 3.7, 1.7. So it tells you that those that are in the urban will test more than those that are in the rural. It could also mean because in the urban, they may have more access to this test kit than in the rural. I wouldn't be able to tell, but that's what this is showing us, and it is significant. So that is what the chi-square tells us. It just tells you the percentage is significantly higher than, significantly higher, than the other. So in running a chi-square, it's easy to do. So how did I run that chi-square? I went to analyze, then I went to descriptive statistics. But first, how did I run the descriptive statistics before the chi-square? I went to analyze descriptive statistics. I choose frequency. Then here, I just put in all the variables that I want to run descriptive statistics for. I put them into these variables, that's all. Once you put them there, you just say, okay, SPSS will just generate all the, to generate the variable name, the frequency, the percentages for all the variables. So that's how I did the descriptive. So how did I do the inferential? I went to analyze, that's for the chi-square. I went to analyze descriptive. Then I went to cross tabulation, analyze descriptive, cross tabulations. Then in the cross tabulations, you have to bring in your main dependent variable in the column. So HIV self-testing, I put it here. Then all the other variables, you can pick all of them, and you can put them at once here in the row. Then you have to come to statistics and choose chi-square, because that's what you want to test first to check for differences in percentages. So you put your chi-square. For the cells, you have to choose role percentages, because you are doing left and right 100%. Like, let me show you what I mean. You see, the yes and the no has to total 100%. So this is role percentages. And that is what you do when your dependent, the two values you have are inside the outcome. So you use role percentages, because the yes and the no are inside the HIV self-testing kit. So you use role percentage, meaning right and left 100%. All right. When you use a column, is if these two values here are independent, like you are talking about like two countries, two distinct things that are not together, then you can use column. And the 100% would be up and down 100%. But for this type, it's left and right 100%. So that's why here, here, when you're choosing this, you do your analyze, descriptive, cross tabulations. Here, you will choose in the cells, you will choose the row percentage. And that's it. Then you said, okay, so once you do that, you see, it's going to give you, See, it's giving you education, no, yes, those that tested, those that did not test, like in the table. Then here it will give you the chi-square and the p-value, you know. So this is how you do your chi-square. So urban, rural, you know, no, yes, gives you the total, gives you the Pearson's chi-square, it gives you the percentages. So that's how you run your chi-square, like what I have here. That's how I ran my chi-square. Now, for the bivariate logistic regression, so this is still chi-square. So for the bivariate logistic regression, for those that are significant in the chi-square, I put them in the bivariate, all right? So, but the bivariate, you have to run it one by one. So before you run the bivariate, you have to choose a reference. Now, for those that have two values, you don't need to choose a reference. It will use 0 as the reference, okay? But when you have so many, like more than 2, then you will have to decide which is your reference. Your reference is the one that usually do not have value, that you would reference the one that has value over the one that do not have value. Like in this case now, from the crude odds ratio, which is 1.06, all right, what do we interpret with this? So the value here is in the male. The female is a reference. So what does that mean? It's telling us that males are 1.06 times more likely or more at odds to HIV self-test compared to females. So the reference doesn't have a value. So you use the value for the main value you are interested in against the value that has the reference. All right. So males are 1.06 times more likely to have HIV self-test compared to the females. If you look at the current marital status, or if you look at, you know, this one that says currently residing with partner, it is significant, but it has a lower odds, not like this one. So for this one, which has a lower odds, that's less than 1. So it would be that those that are currently residing with husband and partner, which is a yes, are less likely to HIV self-test, and you know why. So those that are living with their partner, meaning that those that are married living with their partner, are less likely to HIV self-test compared to those that are not living with their partner, which is the no, which is the reference. Type of residence is also telling us that those that are living in the urban are 2.21 times more likely to HIV self-test compared to those that are living in the rural. So this bivariate that we had done, you know, how do you do it? So I'll show us that then multivariate and we'll wrap up. So for go to analyze, you go to regression, then you go to binary logistic regression. Then in the binary logistic regression, you would have to put your dependent variable. In our own case, is the HIV self-testing. You put it here. Then you can now put all the independent variable, anyone you want to put. But because it's a bivariate, you can only put one independent variable at a time. So you can't put many like you did in a chi-square. The bivariate logistic regression, it will be one dependent variable, one independent variable. Then you can come at the options and choose confidence interval. I think that is all you choose, confidence interval. There's nothing in the category to choose. If the variable has two values, you don't go to the category to choose a reference because it will automatically choose the value that is 0. Because in SPSS, how you code is for your interest value, it is usually coded as 1. The one that is not of interest is coded as 0. You know, like for example, now in this one, my interest is in the male. So I will code male as 1. I will code female as 0. All right. So when you do that, you don't have to bother, you know, to choose a reference because automatically SPSS will just take the 1, you know, as your main variable, and the 0 will be the reference. So once you just put that here and you come to options and choose your 95% confidence interval, I think that is it. You know, you just say, okay. So the last table is the logistic regression. This exponential B, that's the odds ratio. You know, the exponential B is the odds ratio, then you have your significance, then you have the confidence interval, this and this. So in this case, it is 1.28. So what is this telling us? Because our interest value is male. So this is the exponential B, which is the odds ratio. It means that males are 1.28 times more likely or more at odds to HIV self-test, you know, compared to the females, and this is statistically significant. All right. But the approach for like current marital status is different, because current marital status, you have more than 2 values. So in this case, if you put current marital status in the independent, you have to tell SPSS which one is your reference, because it doesn't know. Because why this can be 1 and 0, this won't be 1 and 0. This will probably be 1, 2, 3, 4, 5, 6. That's how you would number it in SPSS. So you have to tell SPSS which is your reference value. So in this case, I'm choosing never in union as my reference value, which is the first. So if I'm going to put marital status now in the model, it will be slightly different. So I'll go to analyze, regression, binary logistic regression. I would remove the sex, then I'll look for the current marital status, which is this. So once you put it here, you would have to go to categorical, move it into the categorical covariance, and choose your reference. So in this case, the reference is first. So you can decide whether the reference will be last or whether the reference will be first. So from what I showed you, it is first. You choose the first, you continue, and you say, okay. Then it will list all of them. All right. It will list the exponential B.
Hi, Felix.
And the yeah.
Yeah, sorry to interrupt, but we are already 10 minutes over time. So
yes, I'm wrapping up now.
Yeah. Thank you.
Okay, thank you. Yeah, so we are wrapping up. So
hello. Sorry to interrupt you. You are going very well, and thank you so much. If we are finished, then I have some queries. Will you
just a second. After this, I just have one more thing, and we're done. Yes. So for the bivariant, so you can see all the values here. It will not give a value for the reference. All right, which is why you have a table like this. There's no value for the reference, okay? Because you choose the first to be the reference. So that's how you would do for each of them one by one. Each of those that are significant in the chi-square, you put them in the bivariant one by one. Then after you've done that, then you can now put everything together in the multivariant. So all those that are significant in the bivariant, you put them in the multivariant pool. That's why here you have the crude odds ratio, which is the bivariant. Here you have the adjusted odds ratio, which is the multivariant. So how do you do the multivariant, which is the final part? You go to analyze, regression, then in this case, you go to multinomial logistic. Then you will have to put your main HIV, self-testing. Then for the factor, you will put all the significant variables at a time. All the significant variables in the bivariant, you put them at a time. That's all you do. You don't even have to touch anything here, and you say, okay. So what it does, it will now tell you the exponential B for all of them, you know, which is what I now representing in a table like this. So this way you will be able to tell. In the crude, it was significant. In the adjusted, you know, was it still significant? Yes, but you can see that the odds had dropped. You know, from 1, it now has a lower odds. So why do you do the multivariant? Just to confirm that your variables are truly dependent. Like, for example, now, look at this one. Can reduce your risk of getting HIV by not having sex at all. You can see there's a higher odds in the crude. But when you adjusted, it was not significant anymore. That's to tell you that can reduce your risk of getting HIV by not having sex, which is a knowledge or awareness, is not independent. It's not standing on its own. So meaning this knowledge, it's actually dependent on something else, they know. So that's why it's not significant anymore. So meaning this particular question is not independent. So that's why you run the multivariate, just to sieve out all the variables that are not independent, that are, what you call confounders, meaning on their own, they can't stand. I think that is basically it. So we've overshot our time, so we'll have to wrap up here. But I needed to show us that. Thank you very much. So I know one person wanted to ask an urgent question. Is that Yedu No?
No, it's me, Vivek Yadav from Nepal. And
Okay.
I would like to ask a very simple question. That I am also doing right now research. My topic of research is prevalence of shift work sleep disorder among the nurses working in teaching hospital. And I have already collected data, and I have entered all the things. What I have done in my methodology, sorry, my English is quite weak, so I just understand the thing. What I have in my methodology, what I have written is that first of all, I'll do descriptive analysis. After that, the directly bivariant logistic regression, where the p-value will be 0.05 less than, will be directly entered into multi-logistic regression. But I haven't done the
The chi-square.
Hosmer. Yeah,
Oh,
yeah.
okay. Yeah.
Neither I have done chi-square test. Actually, I have did my chi-square test, but I have not included in my um, report. And in chi-square test, there was a odd ratio or Rix ratio, and even significance was there also. Yeah, and in my independent variable, total 11 independent variables show the significance. But I saw some Ethiopian research where I found there that they have tested a Hosmer L this test, and directly they have did the bivariant logistic regression, where the p value they have taken is less than 0.25, and those variable which was under the 0. Less than 0.25 were directly taken into the multi-logistic regression. And in multi-logistic regression, they have kept that 0.0 less than 0.05. I have did the same, but I haven't used the chi-square, neither chi-square, neither HS test, that p-value greater than 0.05. Good model fit test. And whether I'm wrong or right, so could you please
Yeah.
explain me?
Okay. Yeah. So I get your question very well, but what I try to present to you is the best approach. Like the standard. A lot of times people can use different approaches, but since we're early career researchers, it's good to present what is usually universally acceptable, right? So most times you can even go ahead, run your chi-square, run your bivariant and multivariant without having to test the model, and it will be published, trust me. But some journals may say, oh, we need to know,
Okay, thank
if
you.
you tested the models first before they are eligible for the logistic regression. So what I would recommend for you, I think if you can follow this pattern, it will really help. Your descriptive, chi-square, significant chi-square, bivariant, significant bivariant, multivariant. So I think that's, that will work. But if you test the model, fine. But if you don't test the model, the paper will still fly. But that is a good practice. If you want to do it, it will be really nice. Yeah.
Okay,
So
one
yeah. So
sorry.
we're running out of time. Yeah. Okay.
Okay, thank you, Mr. Felix.
Sorry, just I want to conclude. So what I have
No,
to
I
do is
think
that
it's enough now. You've taken quite a lot.
Yeah. It's okay. So we
extremely sorry, it's
can.
my career base, so that's the reason. Otherwise, could you share your email? That's what I could.
Yes, I will. Yes.
Okay,
Asta,
that's really
you
good
could,
idea.
yeah, Asta, you could please drop my email in the chat so that they can follow up with me. Yeah. Thank you.
Felix, do you want me to share your email with everybody or just those who are
Yes.
interested? Everybody?
No, you can, yes, you can share for those because we may not be able to take all the questions. Yeah. So,
Yeah, we are
yeah,
already like 17 minutes out of time, and
yes.
it is New Year Eve in Nepal. So
Okay.
another
So,
another thing is you guys can send your question to Felix or to me. You already have my email address. And we are also coming up with short video series in the upcoming days. So maybe we can answer your queries in the video series that will be published in our social media. So one more question and maybe we should wrap up and move towards email. Will that be fine?
Yeah, it's fine.
Okay.
Yeah.
Yes, Mr. Felix. What is the
Yeah.
best model for comparing means of two groups?
Yeah, so the best model for comparing means of two groups is the student t-test.
Okay.
But the student t-test now has independent and paired. So if you're comparing means of independent variable, like you want to look at, for example, mean age between male and female are independent. So that's a comparison of two means. So you're going to be using.
If we are, in case we are comparing like things like temperature, blood pressure, which are continuous variables, their means.
Yes. So if you're comparing them, so it is the student t-test for two.
Okay.
For comparing two means, it's the student t-test. But for three or more means is the analysis of variance, ANOVA.
Is it possible to get an odds in such a case? An odds?
No, you can't get an odds for continuous variable. I mentioned that in the beginning of the, you can't for, if you want to look at like for the continuous variable you have measured, if you want to do a regression for them, then you're going to be using linear regression so that you can see the flow.
Yes.
So meaning if the blood pressure is increasing, is the other continuous variable increasing or decreasing? Yeah, the linear regression would work, but not a logistic. For you to do a logistic regression, you have to dichotomize the mean outcome into two groups. Yes.
So student t-test and linear regression are the best for such case.
Yes, exactly. Linear, yeah.
Student t-test and linear regression. Okay,
yes.
Thank you, sir.
All right, thank you. So sorry so much. I know a lot of persons have questions, but trust me, if you send me an email, I would reply you. And if you are not in the AuthorAID Data Science Hub, then maybe you could join there because we also do some question and answer there occasionally. Yeah. So sorry, I could not take your questions. Thank you. Yeah.
Yeah. Thank you so much, Felix, for a very interactive and very interesting webinar. I enjoyed it so much, and I think everybody has enjoyed it too and learned a lot. We wouldn't be able to take any more questions because we are already like 21 minutes ahead of our time. But there are a few queries that I'd like to answer. Yes, you are going to get the video. We have recorded it. It will be uploaded on our YouTube channel. And there are also previous recordings of Felix in the YouTube channel. Maybe I'll send all the links here. You can see that we have the community of more than 15,000 scholars, and you can join the Google group using that link. We do have Twitter, Facebook, LinkedIn, and Instagram. You can contribute. We are very active on our social media, and we keep on sharing these resources. And if you think that you have some resources that is authored by you, maybe slide or book or by somebody else that you have found useful during your academic journey, you can contribute it on our website. The link is here. You can also contribute your opinions, experiences, ideas, or like the summary of your research via our blog and articles portal. The link is also there. Another is something big is upcoming. Our flagship getting started with writing and publishing your research massive open online course is opening up. It is all free. It lasts for 6 weeks and you learn a lot about writing the research and publishing your research, especially for the young early career researchers. You can just join here. You can see the details there, and in the blog there is a enrollment link. You can email me if something happens, or we have like posted details on our social media also, so you can just grab the information from there. But we would like to see you in our MOOC course. This interesting audience, this interesting learners should be on our MOOC, so please see you there. What else? Yeah, Felix, will you be emailing me your presentation slide, because a lot of our participants are asking.
Yes, sure. I'll do so right away.
Okay, then I will email you the slides and also the recording. Also, let me send the YouTube link right away so that you can access the previous data analysis and data science related webinar. If you type AuthorAID, you'll just find it. But for your ease, okay, here you go. Yes, it was an interesting presentation, wonderful presentation, a lot of good comments. And if you guys are interested, let's take a picture, because we post that on our socials. So please turn on your camera. If you are comfortable, we'll take a picture and we'll end the webinar there. Yes. For those of you very early career researchers, what you can do is, we do have the mentoring scheme on our AuthorAID website. If you go to our AuthorAID website, www.authoraid.info, you'll find the mentoring tab there, and you can find your mentors. Like if you are willing to find the mentors for the biostatistic related thing or writing related thing or anything, like mentor you with a career. If you are working in the field of epidemiology and you want somebody to mentor you or etc., you can just find the mentors there. Okay. Yeah. So this is a very good group of people. So I'll start taking the pictures. Okay, everyone, please smile. Maybe something funny. Something, yes, like that. Okay. I'll move on to next slide. Okay, thank you so much everybody for joining in. See you soon in our upcoming events. For this month, we have massive open online course in 4 days, so don't forget to register. For next month, we have one French tea time with AuthorAID and possibly another English tea time with AuthorAID. Tea time with AuthorAID is a 1 hour long monthly community event of the AuthorAID, where we gather over our favorite cup of drink and then we talk about things, and the scholars from all over the world join us. And yeah, we will have a lot of collaboration, networking, and learning opportunity in the Tea Time with AuthorAID. So see you there. For our Francophone members, we have French Tea Time with AuthorAID. See you then. Yeah, that's all. Thank you so much, Felix. It was awesome having you, like always, and looking forward to many more interactive webinar and tea time with you as well. And everybody, would love to see you in our MOOC and upcoming AuthorAID's engagements. Thank you so much. Bye-bye.
Bye-bye.
Thank you very much.
Everyone.
Thank you.
Have a great weekend.
Bye.
Bye. Bye.
Bye. Thank you very much.
Bye. Thank you.
Yeah, bye-bye.
Thank
Have
you.
a good
Bye.
time.
Thank you very, very much.
Bye-bye. It was very helpful. Thank you.
Thank you. Bye.
Bye.
Thank you,
Bye.
Felix.
Thank you. Bye.